So for me, I think that, we're obliged almost after the discovery of the Higgs boson to aim to deliver really ambitious, unbiased, and broad exploration of the Higgs boson and beyond, for ourselves, but also for future generations of scientists who will have big questions that need answered, and they will need the tools required to answer them.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a wonderful week and have a fantastic weekend in store. Now, this week, we're going to be discussing why particle physicists want to build a bigger, deeper, more expensive particle collider. This week, researchers at CERN in Geneva, Switzerland, submitted proposals for a new, much larger super collider, the Future Circular Collider, or FCC. If approved, it will be 91 kilometers long, more than 3 times larger than the current 27-kilometer long Large Hadron Collider. It will sit twice as deep underground, and it will carry an initial construction price tag of £12 billion. The proposal is for the larger FCC to be built in 2 stages. The first will begin operating in the mid-2040s and will collide electrons and positrons together to produce large numbers of Higgs particles for scientists to study in detail. The second phase will begin in the 2070s and collide heavier protons to create the highest ever energy particle collisions and search for brand new particles. The funding for the project will come from member nations of CERN, including the UK, and some experts have questioned whether it makes economic sense. Some argue that the expenditure is reckless and the money would be better spent in other areas, such as tackling climate change. Others argue that the physics case for the machine is not well motivated, that a new machine is unlikely to discover anything on par with the financial outlay, and that researchers do not have a firm enough grasp on what they're looking for and why. To help me wrestle with these concerns and understand the case for a future circular collider, I'm joined by a set of brilliant special guests. Firstly, Professor Matthew McCullough. Professor McCullough is a theoretical physicist at CERN in Geneva, Switzerland. His work is diverse and touches on such areas as standard model and beyond standard model phenomenology, collider physics, cosmology and astroparticle physics, and quantum field theory. He has done extensive work outlining and explaining the potential for a future circular collider and how it could help us to probe the dark sectors of our universe. We also welcome Professor Patrick Meade. Professor Meade is a member of the C.N. Yang Institute for Theoretical Physics at Stony Brook University. His research interests are focused on physics beyond the standard model and include phenomenological and theoretical aspects of new physics, such as baryogenesis, collider physics, dark matter, flavor physics, and supersymmetry. He is also deeply involved in the push for future high-energy lepton colliders, including a potential muon collider. So I couldn't ask for a better set of guests to help me dig into the case for a new super collider. So there's been a lot of confusion regarding the physics case for a future circular collider this week. I want to jump straight into that positive physics case and start with some higher level concepts. So Matthew, maybe if I come to you first, the initial phase of the FCC project, which is slated to begin in the 2040s, would see the collision of electrons and positrons. This is FCC-EE, essentially a larger LEP, electron-positron collider. Why are we looking to build a lepton collider after the proton-proton collisions at the LHC?
Yes, so the main driving principle, it's not the only one, but the main driving principle is that an electron-positron collider is sort of, I don't know if this is a good analogy or not, but it's sort of like a particle physicist's surgeon's scalpel. It operates in a very incredibly clean environment where you don't have the messy collisions that you have from a proton-proton collider.
Yeah.
So you have a lot of control over a lot of variables. And the reason we want to do it is that we discovered the Higgs boson with the LHC, which is the collider that's currently operating at CERN. But we basically want to take a closer, more careful look at it and try and understand more about what it is, because the Higgs boson is a completely new particle, well beyond any type of particle we had discovered up until 12 years ago when we discovered it. And so the idea of building an electron-positron collider is to really zoom in very carefully in a very controlled environment and investigate what this particle is and how it behaves.
So you've not got any of that kind of proton debris flying around, less jets, these kind of things. It's a much cleaner environment. I guess, can we produce more of these Higgs bosons as well with the proposed FCC?
With the electron-positron collider, no, not so much, actually. It's more that the environment is clean, and we know other things as well, like the center of mass collision energy very well, and the boost, right? How boosted they are in the longitudinal direction and things like this. So it's really the environment that is the bonus, and that enables us to get in and look very, very carefully at the Higgs.
And then just to kind of finish off with the second phase of this. So during the second phase of the FCC, so-called FCC-HH, the tunnel would be refitted with a new machine to collide protons. So this would essentially be a Large Hadron Collider. Why would we be looking to build a proton-proton collider after those electron-positron collisions at FCC-EE? Why is this a kind of package deal?
Yeah, so it's very much in spirit to what happened at CERN before. So we had the large in the LHC tunnel. Many people won't remember this, but before the Large Hadron Collider, which is a proton-proton collider, there was the Large Electron-Positron Collider lab. And that sequence followed a similar logic, right? The sequence there was that the W and Z bosons had been discovered, and particle physicists wanted to have a very close, careful look at them. And so they built LEP, which was a tremendously successful machine, and it really taught us a lot about the structure of certain aspects of nature, namely the electroweak sector of the Standard Model. And then after that, having understood the electroweak sector and had a better idea of what might be going on at high energies, this was followed up with a proton-proton collider, which was the LHC, which was sort of, it discovered the Higgs boson, and it's done an enormous number of other things, exploring at high energies. And this logic we follow the same logic for FCC. So after FCC-EE, which would do the sort of clean, precise measurements of the Higgs and many other things, one would go to the proton-proton collider, which can reach, proton-proton colliders are really like exploration machines. They can reach incredibly high center of mass energies. So would be colliding protons at 100 TeV, but it's actually, they're made up of, they're a bag of particles, right? So the particles that typically collide at energies lower than that, but still they can have a large fraction of that energy. So FCC-HH would explore very broadly up to very high energies. And also a benefit of a proton-proton collider is that they collide lots of different things. So they're very multi-purpose in that sense. If you have some state that can only be produced if you collide like a quark with a gluon or something like this, then a proton-proton collider will deliver that. So it's very broad in terms of the number of things it collides, and it's very deep in the sense that it goes to very, very high energies.
So you're colliding those different things. I guess, given that the kind of partons that are colliding can also have different fractions of the energy, it's searching over a wider energy range as well. So proton-proton, more for discovery and going to the higher energy regime.
And exploration. And also it does very high statistics, because if you don't ask for a huge amount of energy from that proton, then you have processes that can happen at an extremely rapid rate, essentially. And so you can produce a huge number of Higgs bosons and all sorts of other particles, and explore processes that are very, extremely rare in nature, because you have such a large statistical set that if something's only going to happen one time in a million, but you've done it 10 million times, then it'll happen 10 times. Yeah. And so that's another strength of a proton-proton collider.
Superb. Right. So those are kind of the overarching ideas of the project. Let's come into some of the specific physics goals. So one of them, as you kind of nicely teed up there, Matthew, is probing the Higgs boson and its potential, as we'll come on to. So one of the huge physics motivations of the FCC is to study the Higgs boson in detail. Now, the Higgs is a particle at the heart of nature, which we finally pinned down at the LHC, and it and its mechanisms related to it must now be studied in detail. So, Patrick, if I come to you, before we get into the exact details, what are the main questions about the Higgs that we would like to see answered, or theorists would like to see addressed at the FCC? What are the kind of broad ideas before we go into the specifics?
Well, I mean, as Matthew teed up nicely, the Higgs is really a kind of particle that we've never seen before in nature. I mean, it's sometimes people just think of like, oh, we've got this long list of particles. Oh, you've just found another particle.
Yeah.
The Higgs is absolutely unique compared to everything else. It's kind of a one-off, and it also kind of links all the standard model together in terms of it breaks the electroweak symmetry that we talk about, but that's what gives mass to both gauge bosons and fermions simultaneously. So it really is kind of the root of all of our existence. It shapes kind of what the earlier epochs of our universe look like. And as when the LHC originally discovered the Higgs, probably you saw the popular science stories about talking about, is the universe going to blink out of existence? Because it can also kind of shape the future of our universe, depending on what this Higgs potential looks like.
We're going to come on to some of that. Yeah, it's a really nice
the questions about whether the Higgs is actually doing all of the job that we as theorists 50 plus years ago thought is kind of the first question that we want to answer with any of these future Higgs factories in FCC. And also the reason, I mean, Matthew explained nicely that we want to have this two-step process of FCC of EE and HH for discovery and precision. But even for answering questions about the Higgs, like, is the Higgs really what we thought it was? Because it's so different than the W and the Z, we really need a lot of energy and a lot more statistics to answer certain questions about the Higgs. So to fully answer the Higgs questions that we have, we really need this combination of FCC EE and FCC-HH for some of these rare processes, as Matthew mentioned.
Or a muon collider, Patrick. But
there's many different ways.
We'll park that for a second. So one of the key things is probing the Higgs potential. So Matthew, if I come back to you, like I say, one of the key aims of the FCC is to probe the Higgs potential. What is the Higgs potential for people who are out there maybe a little bit confused about what the Higgs potential is? And why is it so important that we probe its shape and its properties?
Yeah, it's a really good question. Just to come back to the last question, I would like to part. I don't know if we'll come back to it, but an important question as well is Higgs compositeness. And I don't want to.
We are going to come back to that. Don't worry. That is something I've got later on.
So the Higgs is a field which is something that exists everywhere and can take different values. So you can think of it. This is a crude analogy. So don't start trying to poke holes in it because it will fall apart. But
we can have Mexican hats. We can have bottoms of wine bottles. We can have whatever you like.
No, I'm not even going to touch that. But so, if you're in a place, one thing that you can measure that has a value is the temperature, right? And so the temperature could be different in different places. But you can think of that as being like, again, it's not a great analogy, but you can think that, take that analogy, and the Higgs is sort of like something, it's a field, something that you could measure, and it could be different in different places. But on average, across the universe, it has some average value. We call that the vacuum expectation value. And if we were to change that value, the average energy density in the universe would change. And how much that changes is dictated by the shape of the Higgs potential. If I crank up the Higgs field, the total energy density will increase, and that's measuring the shape of the potential going that way. If I were to wind it back and sort of slowly switch it off to smaller field values, then the energy density would also go up, and it is sitting in this local minimum.
I think I have some nice pictures here.
Yeah, right, exactly. It's sitting in this local minimum. I don't like this picture, by the way. I like the one. I like the one on the right. I like the one on the right.
We got other ones. Maybe this one.
Yeah, that's good. That's
all right,
good.
We'll go with this one.
I won't take issue with that. And so if you look at our vacuum, it's not exactly at zero, where it shouldn't be in that picture.
Yeah.
And so measuring the shape of the Higgs potential is telling us how essentially the energy density of the universe depends on the value of the Higgs field. Now, what's really neat is that we're sitting at a certain value, and all we can do is sort of perturb around it. We can give it a little shake, but we can't actually, in all the universe, change the Higgs value and see.
So all we kind of know is that we're sat in a local minimum, and it's kind of roughly parabolic about this position, but we're not sure what's kind of further out.
But the really neat thing is there's a one-to-one correspondence between the interaction between certain n Higgs bosons and the nth sort of moment in some sense of this this potential. So if you were to do, you may have, I'm sure not all of your viewers will be familiar with this, but I'm sure some of them will be. If you're to do a Taylor expansion about the minimum of the potential, then each term in that Taylor expansion corresponds to a Higgs self-interaction. So
okay, yeah.
Cubic term tells you about the Higgs cubic interaction, so 3 Higgses, and so on and so forth. And so,
so if we can look at these multiple interactions of multiple Higgs, they link back to the shape of that potential. We can probe that shape potentially.
Precisely. And so, but the shape of that potential, as Patrick just said, has very, very deep implications for some big questions in physics. So the shape of that potential is related to the way the Higgs field turned on, essentially in the early universe. We call that the electroweak phase transition. And that's the moment it got an expectation value, and that expectation value gave mass to a bunch of particles. But also, if one makes some further assumptions, then the shape of that potential going out to very large field values could have implications for the distant future of our universe. And so it's really super important to measure, just on a scientific basis, to try and understand what is the shape of the Higgs potential. And the way to do that is to bash Higgses off themselves.
And I guess that requires higher energy, a cleaner environment. Patrick, how do we produce these? Because these are very rare processes, right? I think I'm not exactly sure of the number of times a Higgs boson gets produced in a LHC collision, but if you're wanting to produce 2, 3, 4 in collisions, this is going to be an incredibly rare process.
Yeah, I mean, if you even like for our best laid plans for things like FCCHH or high energy muon colliders, we're basically just able to scratch getting 2 out. Getting 3 out becomes really hard. And I mean, this is just, like sometimes people talk about like, well, these projects are getting so large and so difficult and so costly. But at the same time, like what we're really talking about, as Matthew says, we're taking this vacuum we live in and we're trying to bash it at its most fundamental level and excite multiple Higgs out of it.
Yeah.
And so these things just are very rare processes that require a lot of energy to be put into the system and sufficient statistics, which is why these projects eventually get so large.
I think I've got here it's 1,000th of the rate for 2 that it would be for a single Higgs, and that's already difficult to produce a single Higgs. So it's going to be very, very difficult. We need higher energy, higher luminosity to get enough statistics to look at these processes. Is that fair, Patrick?
Yep, exactly.
Okay, so and Matthew, you mentioned there just so people understand that this could have implications. So the importance of looking at this could have implications for how the universe might end. So could you just tell us a little bit more about that, maybe from the start?
Sure. No, I should, I don't know if you have any graphics, but now's the moment to put the big flashing disclaimer.
We can say that. Yeah, we can, and I can edit something in that kind of, a flashing siren and some noises. So
the standard model of particle physics, which is just our current working theory, you can buy t-shirts and mugs with it on, is not complete. So we know for various reasons that it will break down at some high energy scale, i.e. some very small distance scales. It is not an adequate description of nature. But we don't know entirely where that will happen, where the next layer of nature, if you think of nature as like peeling back layers of an onion, right? We had the periodic atoms, then we found out atoms were made up of electrons and nuclei, and then we realized the nuclei were made up of neutrons and protons, and they're made up of quarks and gluons, and so on. And so we don't know where that next layer of the atom is. But if one makes the assumption that that next layer of nature is, if one makes the assumption that that next layer of nature is at extremely small distance scales, so very, very high energies, then you can extrapolate what the standard model predicts up to very small distance scales until that thing kicks in. And there's actually a sort of an intermediate field energy, so there's energy density carried in the Higgs field. And if you take the standard model, just that assumption, nothing else for a large range of energy scales, and you increase the Higgs field and just take the standard model, then with the central values that we currently measure for all of the parameters in the standard model, it looks like it turns over again, which is this picture you have here in the middle. And if it turns over again, then and goes to a lower minimum than the one we're in, then in principle we could tunnel out to that minimum. Now that would never. That's not. That's not going to affect. Anything on a human timescale or even on a solar timescale, but well, probably not. But it's a very interesting observation. And by measuring other properties, so by measuring the other properties of the standard model, like the top quark mass, then we can pin down, it gets its mass from the Higgs, so we can pin down how strongly it interacts with the Higgs and so on. Mm-hmm. Then we can extrapolate further and more accurately and really understand this process. However, as I said, there's a big disclaimer, which is that's only if you assume there's nothing else up to those very high energy scales. And there's no reason to believe or not believe. Well, there are actually some reasons to not believe that would be all there is. And so it's under a specific hypothesis, but one needs to remember that hypothesis when discussing.
And I believe, Patrick, so just for people who are wondering, why is this useful? Why do we want to do this? It is fundamental physics, and we want to understand the shape of this potential, but also understanding the shape of this potential, it feeds into a lot of beyond standard model theories, right? That a lot of beyond standard model theories predict modifications to the shape of this potential. So it's important to understand it because it's going to constrain the theory where theory goes next. Is that fair, Patrick?
Yeah, and coming back to the point Matthew raised about compositeness earlier as well, I mean, one of the things that I think probably lay people don't realize is when we talk about the Higgs and having discovered it, the Nobel Prize has been awarded, and we've found the last piece of the standard model. From the perspective of quantum field theory, the language that we use to describe all of nature at these short distances, the Higgs potential really is kind of the Occam's razor, simplest, dumbest explanation we could have come up for explaining the standard model. These sorts of things have been manifested in other areas of physics. The classic example is the so-called Landau-Ginzburg model for superconductivity, where a similar phenomenon of that the symmetry gets broken away from the origin in this picture happens as a nice phenomenological description of why superconductors can exist. But very quickly after, they realized that one of the types of these superconductors could be described by some underlying dynamics. So this is this BCS theory of Cooper pairs condensing to create this superconductivity effect. And in most every other scenario where we see this effect of symmetry breaking in field theory, we've always found kind of an underlying microscopic dynamics to describe it. Whereas the Higgs is just taking this simplest picture, the simplest field theory we could write down that does everything, and we don't have any clue for why it is the way it is. So a lot of the theories that we think about for beyond the standard model of physics are trying to explain the properties of this potential, why it makes sense in field theory, and it can come in different forms of, it could come with some more underlying space-time symmetries, things that are called like supersymmetries, or it could be something more like Cooper pairs where you had some underlying composite dynamics of the Higgs field. But as you said, in most all of these theories where we try to actually address what's causing the symmetry breaking and if there's a origin to why the Higgs potential looks that way, there's other dynamics that tends to modify this potential. So beyond just abstractly double checking if the standard model is correct, trying to actually understand if there's an underlying theory of nature that explains the Higgs is completely connected to our experimental pursuit of testing the Higgs potential as well.
So we know we've kind of, or we're quite confident we kind of rolled down this hill into this minimum, but and we found the Higgs, but we've kind of not done much else beyond that as yet.
And we don't even know if we rolled down the hill.
Okay.
We know we're at a minimum, a local minimum.
Yeah. And that's it. So lots and lots of work still to be done. Okay, excellent, good. Let's move on to the next part. So another thing that we want to nail down, Matthew, with the SEC physics program are the Higgs couplings with far greater precision. So what do we mean when we say we want to measure the Higgs couplings with far greater precision? Is this all about testing whether the Higgs boson that we see is the one that's predicted by the standard model, or are we going beyond that?
Yeah, it sort of goes beyond that question in the sense that, like I said, the nature, as we've explored it through going to smaller and smaller distance scales, building more and more powerful microscopes, right? Colliders are really one should think of them as microscopes, is that there are layers and layers of nature, and we sort of go through a chain of what we call effective field theories, where we have the right working description for phenomena at some energy scale, at some distance scale, but then it gets replaced. Okay, one example would again be atoms, right? If you're probing atoms with light with a wavelength that's much, much longer than the size of an atom, it doesn't make sense to talk about its constituents.
Yeah.
Similarly, if you're probing a nucleus with electrons at very low energy, then it doesn't make sense to talk about the protons and the neutrons. It's more useful to talk about a nucleus with a charge, maybe some spin, some moments, things like this. And so we don't know that there's no reason to believe, in fact, that the standard model is the last fundamental layer of nature. And so we want to understand what comes next. And the way to ask that question, and one example, as Patrick mentioned, is like, for example, if the Higgs is composite, or if the Higgs happens to interact with other particles that we just haven't seen yet, then those properties would get encoded on slight deviations from the standard model. And so by measuring how the Higgs interacts with B quarks, for instance, or the Z boson, or any of the other interactions that you see on this plot that you're showing, it's not so much that one is, well, I guess it's possibly a question of philosophy, but one is actually, by measuring those properties, those interactions, you're actually exploring. You're exploring possible physics that could be going on involving the Higgs boson in a way that's different from just going to higher energies and trying to create particles. So it's a mode of exploration. So for me, when I see, a measurement of the Higgs coupling to Z bosons, for instance, in my mind reads that as, well, if the Higgs is composite, then the size of the Higgs, the composite objects that make it up, are existing at, say, energies maybe 6, 7, 8 times greater than the mass of the Higgs boson. So they're sort of pretty small if it is composite. And so that's really, it's a mode of exploration. We call it indirect exploration, but it's extremely effective, and it's a mode that's worked very well in the past as well.
So the standard model, would predict that the Higgs boson couples to these particles with a strength that's proportional to their mass. But if you can see deviations from this line, that could potentially give some clues as to where beyond standard model physics is hiding. Is that kind of the idea, Matthew?
Indeed, and not seeing those deviations,
is
what isn't happening as well. So every measurement you learn something, but it's not so much an exercise in trying to sort of, well, again, it's maybe depends on perspective. It's not so much an exercise in sort of trying to confirm the standard model. It's really more that this process is exploring what's going on at tiny distances.
And why, just Matthew, to close this section off, why do we need the FCC for this over the LHC? Why can we not get the precision that we would like with the LHC? Why do we need this larger collider ring? Is it again the clean environment and being able to measure these couplings with more precision?
It's because we're sort of left a little bit. We will, unless we see something unexpected at the high, in future LHC runs, we're going to be left a little bit hanging in the dark, in the sense that the LHC is a fantastic machine, and it will measure certain Higgs couplings to very good accuracy. 1.5%, 2%, something like that, to the Higgs coupling to the Z boson, for instance. But that's sort of insufficient. That's around the ballpark. If one even takes the standard model, this is sort of a very broad brush statement I'm going to make, but if one takes even the standard
I'll put the
model,
disclaimer up again, don't worry, it's fine.
Oh, I don't think this one needs a disclaimer.
All right, okay, smaller one, less silent.
Even if one takes the standard model and calculates the quantum corrections to the way it interacts with the way the Higgs interacts with other particles, then because it's not charged under the strong force, those quantum corrections tend to be around the size of, say, 2 or 3%.
Right.
compared to the leading order predictions. And so if we're only measuring things at 2 or 3%, we're not actually probing the quantum nature of the Higgs at all. Whereas we want to jump, with FCCE, we want to jump by a factor 10, basically, deeper into the Higgs. And so then you're probing not only the sort of the classical, as we would call it, predictions of the standard model, but we're actually probing its quantum structure. And then anything that could show up at the quantum level, we would hope to be able to see it. And so that's the reason there's a sort of a threshold that one needs to cross, and going well below, not just a bit, but well below the percent level is required.
Yeah. Once we found this thing, we need to go down to that lower level. Patrick, the next thing I've got on the list of things we want to know about the Higgs is improving our measurement of this is a little bit zoomed in. I can zoom it out a little bit. Improving our measurement of the Higgs width. So what do we mean when we say we need to measure the Higgs width with greater precision? And is this about understanding how the Higgs decays and what rates it decays to various different particles?
Yeah, I mean, one of the things that we think about of what a width is for a particle is these are kind of the quantum ways that this particle can disintegrate into other particles. And so by measuring the actual width that is on this screen right now, we can essentially inventory all the possible ways this particle decays. And even if we can't see the decays in terms of like experimentally finding the particle to decay into, whatever contributes will change this overall width. So it's a very powerful way to study whether a particle has any other interactions that are very hard to see experimentally in a direct fashion.
I think we've seen some studies into the invisible decays potentially, or bounding those invisible decays.
Some decays can be invisible within the standard model, but there could also be interactions of our Higgs because it's such a unique particle that the Higgs could talk to other sectors that could be out there in the universe, dark sectors. And so by being able to measure the width, even if we can't see these other sectors experimentally directly,
we know something's going on which isn't in expectation.
We can really understand how much could be going on elsewhere. And there's a very nice analogy of this with the LEP. This one, as I think Matthew said, some people might not even remember LEP. But we did this with the Z boson as well, where the Z can decay all these particles. And for instance, neutrinos are an invisible particle that you don't see at the LEP detectors. You see it kind of as a missing part of the event. And we were actually able to do at LEP by measuring the width of the Z boson. We were able to say, yep, we're really sure there are 3 neutrinos rather than possibly many more invisible things that the Z was decaying into. So by measuring the Higgs width, we can ask these same sort of questions of, does the Higgs have any other interactions that we didn't know about, or are the couplings modified? And the problem is at the LHC, the environment is just such that you're not going to be able to do this measurement because you have so many other things going on. You don't exactly know what the center mass energy. And last but not least is the width of the Higgs is so incredibly small that unless you have a very clean environment, you're just hopelessly lost in terms of trying to make this pretty shape that you have shown on the screen. So that's the goal of E plus E minus machine like FCCEE, where you could do these very precise measurements and just understand, could the Higgs be talking to anything else, and what is the Higgs width?
I think if we look at I don't know if this is the latest measurement. It's April last year, so it's not too long ago. I think the expectation is that Higgs goes to 4 neutrinos 0.1% of the time, and we still have 10% of Higgs decays unaccounted for. So that leaves a huge kind of region there potentially for beyond standard model physics to be hiding, right, Patrick? We haven't been able to close that down at the LHC yet.
And I mean, people always talk about just general BSM physics, but again, coming back to this point that the Higgs is so unique, the structure of the way that the Higgs is as a spin zero particle naturally allows it to talk to other particles very easily compared to having a fermion having this extra invisible part that would be at low energy. So the Higgs we're very far away from testing. As you said, we have orders of magnitude to get to even like the invisible part of neutrinos. Mm-hmm. So there could be lots in there, as well as it's very easy to understand theoretically how these other things could be there for the Higgs.
So it's a very, very powerful probe of potentially things that are hiding for beyond standard model physics. Matthew, I'm going to come back to you because you've been kind of mentioning the compositeness quite a few times. So I want to come to you on that. So Higgs substructure. So another key aim of the FCC physics program is to determine whether the Higgs is a fundamental particle or has substructure. So what do we mean when we're saying the Higgs is composite? It's a fundamental particle of nature, no?
So I'm
guessing the answer there is potentially no.
I mean, I would probably say probably no.
Okay, good, right. I like it.
The scale is when one has a fundamental field in a quantum field theory, that's usually a placeholder, because as I said, it's quantum field theories tend to be, there are some that are just, we call it UV complete. They just go the whole way up to arbitrarily high energies, the whole way down to arbitrarily small distance scales, and they don't need to have another layer. But that's not the case with the standard model. And so they are layers. And normally when we have call something a fundamental field in a quantum field theory, that's a placeholder which is valid up until that replacement happens. So for instance, one could work, I don't know if you're familiar, I'm sure you're familiar with pions, but if your viewers may not be, pions are particles that are made up of a pair of quarks, a quark and an anti-quark, and pions are quite light. They're the lightest particles we know that are made up of quarks. They are composites. One can study the theory of the theory of pion scattering and all sorts of things at low energies, with a theory in which you treat them as fundamental particles with a lot of interactions. That doesn't mean
I guess it's like atoms again, right? If you're at low energy, you can just treat it as a blob of positive charge, but when you get to very high energies, we need to be talking about the quarks and gluons and things that are inside. So it's different layers again. Exactly.
And so although we work with the working definition of the Higgs in the standard model, the thing on the t-shirt has it as a fundamental description, that does not imply it's fundamental up down to the most microscopic scales of that one could imagine. So anyway, and so we want to, I think it's very plausible that the Higgs could be composite. In fact, we've peeled back so many layers that to me it would sort of be very surprising. Who knows, right? This is just postulating, but to me it'd be sort of surprising if the standard model particles are not composite to some extent or another. And so we want to ascertain if that's the case or not. Now, there are many different types of compositeness that the Higgs could have. Also, there are types of compositeness where particles aren't super composite. They can be sort of quasi, we call it partially composite. And so there are many different facets to this question, but we would like to know, especially because up until now, all of the scalar bosons that we've discovered in nature have been composite. So it makes sense, right? You discover another one, you want to know if it's composite. And so we want to answer this question. And as I said, the way to answer this question is by measuring the Higgs, at low energies, is by measuring the properties of the Higgs boson very precisely, because that compositeness gets encoded. And the way I would describe that, the way it's encoded, is that if you take a neutral atom, so it has no electromagnetic charge.
Yeah.
And you would scatter
a get Van der Waals or something out of it, though.
Right, exactly.
There's stuff underneath, right?
Exactly. So this is the point. So you scatter a photon off it, and if the atom was really a truly point particle, nothing would happen. It's neutral. That's the end of the story. But in actual fact, an atom has substructure, right? There's electrons whizzing around this nucleus and so on. And that substructure is encoded in interactions between the atom and the photon that are not just the normal interactions you would have if a particle is charged, like between an electron and a photon. And so photons will scatter off atoms in a certain way, but that scattering might be suppressed. But if you can measure, those processes extremely precisely, you can start to infer things about the substructure of the atom, the fact that it's composite. And it's exactly the same story for the standard model. In fact, so the standard model as written on the t-shirt is just the first line in some sense of this story. And then any potential compositeness, or actually even if the Higgs isn't composite, but it has interactions with other new particles, that gets encoded in these sorts of interactions, which can be considered to be like an analog of dipole interactions or multipole interactions. And so those interactions would imprint themselves on how the Higgs interacts with other particles. And so we would hope to see them. So that's really how we would go to chase towards finding out if the Higgs is composite.
Brilliant. So I guess there's a lot of theoretical predictions about how various composite Higgs would behave and how they would interact with other particles. And therefore, if we have the precision, the higher energy at an FCC, we could probe some of those theoretical models. Is that kind of where we're looking?
Yes. And so there's a great variety in the sort of predictions they make, but there's one thing that sort of sticks, which is that there seems to be, for the majority of these types of models, a correlation between how far away you can push that compositeness scale, the magnitude of the deviations that you predict in the standard model, or in the Higgs couplings to standard model particles, and actually how much we say fine tuning, but basically how much you have to twiddle the dials in that composite theory to keep the Higgs light. It doesn't want to be so light. We have a way, the pion is much, much lighter than the proton. And we actually have a really slick way of understanding why that is. And it's a very fundamental reason, which is related to symmetries. And that reason will only work by analogy with the Higgs boson, for instance, only so well. And beyond a certain mass gap, one needs to nature would have to have dialed the parameters in its theory to try and keep the standard model, the Higgs light. And so that makes us think when a theory requires that, a lot of fine tuning of parameters, to us, that makes it seem less plausible. And so this is why I think going to sort of the percent and below level is so important, because there's only so far you can run, which means that these deviations can only be so small before you would start to pick them up.
Good. So we want to get down to those levels of precision. Patrick, if we move on a little bit from the Higgs, because the Higgs is incredibly important, so we spent a decent amount of time on it. But so the Higgs program alone is incredibly, incredibly rich. But another major physics motivation is to probe the standard model to unprecedented precision and drastically improve electroweak precision and flavor physics measurements. So, Patrick, why is it important that we probe the standard model in even greater detail than we have thus far? I guess it's kind of the same answer that we've had throughout this discussion, that we can see deviations.
Yeah, I mean, I think really coming back to this idea of microscopes probing for these extra layers is kind of the common theme, where the Higgs is an important aspect of everything we do, but just like telescopes can look at lots of things, microscopes can look at lots of things. And what we really want to try to do is just use all of our different probes that we have out there to push to the shortest distance possible. And because many of these questions can be related, but there might be different mechanisms at play to, for instance, explain why we have this big hierarchy of mass of the particles that you have showing, or why the particles have this very weird mixing pattern that they have. So we'd like to use all the probes available. And one of the really exciting parts of FCCEE is that it has other run plans other than just running and looking at single Higgs properties, where we can make incredible advances under what you mentioned as electroweak precision. So this was done in the past with LEP, where they were studying the Z boson. As Matthew said, this is kind of the analogy of going with FCC from LEP and LHC. And one of the things we really knew from studying the Z boson very well was that we were pretty sure that at the LHC, something Higgs-like was probably going to appear. Now, the notions of how composite the Higgs could have been, et cetera, was a little bit more vague because we haven't found the Higgs as of yet. But by using these very precision probes of a different part of the standard model, it really allowed us to know a lot about what else could be there. And then that's why I don't think anybody was very surprised that we found something that looked Higgs-like when the LHC discovered it about 10 years ago or so. So now we have the ability with FCCEE, if it's built, to make these other kinds of measurements that we've done at other machines and other experiments. But the way that the machine is set up with the current technologies, we can go many, many orders of magnitude beyond what we probed in the past. So whether it's understanding the properties of the Z boson, where we'll have essentially 1 million times more statistics than what LEP had almost.
Yeah.
Or properties of flavor physics, properties of B quarks, where we can have an order of magnitude more B quarks than these super B factories that is now currently running in Japan. So it really lets us probe the standard model in many different ways to try to peel back the onion and see what are the underlying causes for why the standard model looks the way it does.
I think, Matthew, you've got a really nice table of kind of the quantum leap, if that's the right word, of precision that we could have with this machine. Do you want to tell us a little bit about some of these parameters that we could drastically improve with FCCEE?
Yeah, so all of these parameters encode various aspects of what Patrick was just saying. So by measuring them, you're sort of probing what's going on at shorter distance scales. And the really remarkable thing, so this just puts numbers to what Patrick just said. So I guess I don't really need to say a great deal, but if you compare the current error.
I thought I'd better bring you back, seeing as it's your table. I could have let Patrick roll.
It's not my table. I didn't make this.
You stole it from somebody else. Okay.
Yes, exactly. Yeah. But if you look at the current error, for example, on the Z mass, that's the first line there.
Yeah.
And then you look at FCC. You should always take, essentially at the moment, these numbers, especially the systematic. So those are related to things like how well we can actually calculate the standard model predictions, how well we can measure certain other parameters that go into the recipe, essentially, of extracting these measurements. And so you should always take the bigger of the two between statistical and systematic. But you see for MZ, you do more than an order of magnitude. For some things, there are other tables that are even more impressive actually now, as more things are being calculated. And so every single direction is probing and exploring a new direction of physics that could exist beyond the standard model in a different way. And it's really remarkable. It's a very exciting part of this program. The European strategy sort of that occurred a few years back sort of highlighted that we want to explore the Higgs, and we want a Higgs factory. And so this is just a very positive spin-off that if we built this FCCE, we could also do this thing, and actually runs at higher energy, producing top quark pairs and so on. It's really a bit of a Swiss arm. I said it's a surgeon scalpel, but maybe one of them is a surgeon scalpel, but it's really a Swiss Army knife of precision physics. And so and each component of that Swiss Army knife can answer different questions.
Patrick, do you think, just sort of before we come to the end of this part, and this is something Martin Bauer talks about, he couldn't unfortunately join us today, but do you think particle physics is held to a kind of unfairly high standard where precision work like this isn't valued as much as discovering a new particle? So this kind of gets lost in the kind of excitement.
I mean, I think sometimes that part can get a bad rap in the sense of people think of it's more confirming. Some people do it just to kind of confirm the standard model, or some people just really like making measurements and they'll make it more and more precise. I think the problem, though, even larger, is that because it's such a complicated subject to understand the language of quantum field theory that relates all these different things. And so doing precision physics is doing discovery physics. And at the same time, doing discovery in high energy physics is understanding what could be showing up in precision physics. So all these different things are related, but yeah, depending on how it's spun as a PR wise, it can be sometimes one can look sexier than the other or vice versa. But I think one thing that also does get lost is that these are not independent, right?
Yeah.
Ways that we search nature, we're still using the same language of quantum field theory to describe this all. And so it's not a matter of, hey, I'm a physicist that really likes precision, I want to do this there. hey, I want to smash bigger and bigger things together, I'm a discovery physicist, they're really all linked together. And I think because it's such a complicated subject, even physicists within our field don't necessarily understand how linked sometimes these things are, or what the implications of precision for the shortest distances are, or what the implication of search for precision are. So it's a hard field. It's hard to explain.
I feel like it kind of, but when I see things like this in the FCC physics program, for me, it kind of puts a bit of a lie to this idea that particle physicists are kind of flying blind. They don't know what they're looking for. The reason that we're doing these precision studies is so we know where to look for. We know where the deviations are. We know where the potential cracks are, right? So it just seems to kind of push back against that idea, Patrick.
Yeah. And I mean, as we know, precision physics, we've come to revolutions in physics via doing precision measurements. I mean, it's not like we just smashed things together and then found the protons and neutrons. That's not the only way that we've done discovery physics. I mean, I always like the analog of for cosmology, where people in the public are much more attuned to like pictures of the universe and thinking about the universe than they are the shortest distance scales. But it's like we knew for many, many decades the universe was expanding. I mean, back to the era of Hubble. And only by doing more and more precision measurements do we find out many decades later that this expansion was actually accelerating. And we had a revolution in understanding of that there could be a cosmological constant or dark energy or things like this. So precision physics is really an important part, and it can have these revolutionary consequences just as much as quote unquote discovery
finding
physics.
a new shiny toy to have a play with. Yeah. Very interesting. So, Matthew, this is another nice topic, and sometimes people just they get riled about this because they think they're just saying, "Oh, they're going to find particulate dark matter again." But probing dark sectors is another potentially important thing that FCC could do. So, a huge physics motivation of FCC is studying these so-called dark sectors in both breadth and in detail. And this is something you bring up in your talk. So what do you mean when you say probing dark sectors? What are we talking about, and what are we looking for here?
Sure. So first thing, I'm going to go into announce my own disclaimer, in the sense that this is not a huge component of the physics program. This is like a spin-off.
Even though it's the first thing in your talk, but yes, okay, good.
Yes. Well, no, but that was a talk. That was a talk. I know
to a particular audience. No, I'm being.
Well, we're also where it was requested that I talk about things in.
Right. I'm being a bit naughty. Sorry.
Yes. No, absolutely. But so I'll talk about the philosophy in a second. But in terms of the physics motivation for these machines, it's not to discover dark matter, right? It's all of these measurements that we've just discussed about the Higgs.
Exactly. Yeah. That's important. That's important to know, because in those BBC articles and things we've had this week, we're going to find dark matter has been very front and center, and that's not the things that we've been talking about are really the motivating factors.
Yes, exactly. The motivating factors are really to explore this new Higgs particle and understand what's going on there, and all these other measurements that Patrick mentioned, the precision electroweak. But it is possible that, it's not, there's no guarantees, but it is possible one could open windows into dark sectors. And I'll explain that in a bit more detail. So first of all, again, a bit of philosophy, my personal philosophy. Not all theorists would agree with me. I think Patrick probably would, but I don't think everyone would.
I'll see what you're saying then.
Yeah. It's okay. If next time we can bring you back with someone really, really confrontational, but we'll go with it for now.
So when I look at the standard model of particle physics, it makes up like about a fifth of the matter density in the universe. I'm not talking about dark energy here. I'm talking about matter. And within that sort of fifth, don't hold me to exact percentages, but within that sort of fifth, there is an enormous wealth of phenomenology. There's a lot of stuff that goes on, right?
Atoms, and then lattices and wider,
crystals, planets, all the way up, in my view, to neutron stars, which are like great big nuclei held together by gravity. And so I sort of find it really hard to imagine, and this is just bias, okay? But I find it really hard to imagine that other four-fifths of
It's
the
just
stuff,
it's just one particle
it's
bashing
just
off
one
things, and that's
particle and it
okay.
doesn't have any mates. It just floats around. And so personally, I think, even if one is, I think discovering dark matter might even be the wrong bar to hold oneself to. I think there could be, in terms, one should hope, in my view, to understand the phenomenology of the dark sector. And the phenomenology might be dictated by particles that aren't stable. They might just be, we know there is a dark sector. We know it interacts with us very weakly, certainly via gravity, but other interactions must be quite weak. But how we would reveal those interactions might not involve, seeing dark matter itself. Yeah. And one could say the same thing about the universe, right? And the visible sector. The mass density is mostly hydrogen. If you assumed that hydrogen was all of the phenomenology, then you get everything wrong, right? We see the universe through photons. They make up hardly any of the energy density of the universe, right? And so I think one needs to be open-minded. Now, something that's about things that are interacting with us weekly. So if you think interacting with us weekly, you might think, very rare events that happen only very rarely. You need to do something lots of times before you see this one event. And events that might look very exotic. If you might have particles that are so weakly interacting with us that they're long-lived. Once you produce them, the interaction is so weak that it takes them a long time to decay, and so on. There's a huge, open field of possibilities there. But as Patrick alluded to earlier, the Higgs being a scalar, so not having any spin and not having any charge, it makes it really easy for the Higgs to interact with other sectors. It's one of the easiest, we call it a portal. Yeah. It's one of the easiest ways it can interact. And in the jargon, we say it has very relevant interactions. You can get, quarks, for instance, could interact with other neutral particles, but they tend to have interactions that if they're generated at high energies, by the time you get to low energies, they're extremely suppressed. Whereas that fall off happens much more slowly with the Higgs. And so the Higgs is again special in some respect, and maybe that could open, as I said, there's no guarantees, and this is not the core physics program of FCC. Yeah. But it's possible that then by studying exotic properties of the Higgs, we might uncover something. For instance, this table that you're showing now is a very nice table. It's actually quite old now. I guess it's probably about 8 years old. But people have studied, say the Higgs can decay into pairs of very weakly interacting dark sector particles that are not necessarily the dark matter. Then because the FCCE is such a clean experimental environment, even if it decays into particles that are sort of hard to tag in a proton collider environment, like charm particles and so on, even if that's the case, one could actually probe those possibilities down to very, very small branching ratios of the Higgs, so very, very weak interactions of the Higgs with those new dark sector states. Maybe even those dark sector states could decay into dark matter itself.
And I guess that plays back in with the width measurements and things. Maybe these things are hiding in there, and we can go looking for them more directly, maybe.
That's a component of it, but you could also hope to see them explicitly, decaying in your detector. Maybe one of them. I'm talking about pair producing these dark sector particles, which are stable. They're not the dark matter, but maybe you could have events where one of them decays to dark matter and one of them decays to something we can see. And as you can see on this bar chart, SCCE would really dig deep into that territory. So we're doing, again, it's a question of exploration. Exploration, there's no guarantees, but it's exploration, and one could hope to dig deep into the dark sector. Now, it's possible that the phenomena of the dark sector could arise at different energy scales, right? We really are very ignorant of what's going on in the dark sector. And so there's really no guarantee that it even lies in this window. But if it does happen to lie in this window of energies, then this is a really great way to go after it. If the physics of the dark sector is associated with much lower energy scales, you do different sort of experiments. Yeah. But here, the FCC is very unique. We would say that its intensity frontier machine, especially from Z decays as well, is a really great way of probing exotic dark sector physics. It's the only intensity frontier machine that could operate at energies well above what we would traditionally call intensity frontier machines. It sort of covers a window that no other facility can cover.
Mm-hmm. So very
Patrick wants to add anything. 'Cause I'm not
Patrick,
sure.
please, yeah, if you want to come in.
No, I completely agree with everything Matthew said. Maybe just on a completely separate note, when Matthew was bringing up how this is not the main core part of the program, I think just thinking back to the topics we already touched, it really emphasized this concept that a collider is not just a monopurpose, turn on, yay, did we see something, nay, did we see something. We have all of this physics in the same machine, and we can go after trying to explore nature in so many different ways with one experiment, one gigantic experiment, but one experiment has essentially thousands of different types of physics experiments within it.
Yeah. And that's a very, very important message. And I want to come on to a little bit of that kind of how people are reacting to this potential machine. So we had the kind of article that kind of prompted me to get you guys together was this one in the BBC, which I didn't think was great. So as we come to the end of this discussion, I want to switch gears slightly and discuss that potential mismatch between the physics case that we've discussed for this new collider, a new collider like the FCC, and the public perception of that physics case. So Patrick, maybe if I come to you first, do you think that the building of a machine like this, and we've seen a little bit of it on Twitter, has a kind of PR problem with the public? Is that real physics motivation for a new collider that we've talked about misaligned with the public perception of the physics case? Do you feel?
I do think it's a little bit misaligned, and I mean, it's probably a bit of our fault in terms of communication, because it's very easy for somebody who works on JWST to throw up pretty pictures of what they're seeing out in the universe or a galaxy or a solar system. And even if people don't really understand the concept of like studying the physics of molecular clouds or something like that, they see the pictures and it's there. Whereas for us, we have just as important a physics case as any other major science project in the entire world, from my personal view. And we have a very broad physics case for it. But it's sometimes very hard to make this connection of explaining exactly what we want to do and exactly what it means to say, like, oh, well, if we get this extra precision, that's going to mean opening this layer, this onion a little bit more. Yeah. So I do think there's a little bit of a misalignment right now, but it just comes with the territory that, I mean, trying to explain to a public where like people barely know what an atom is made of if you talk to a very generic person on the street, let alone trying to explain these subtleties of, well, the Higgs boson actually could be composite. So I think there is a public.
I mean, even for someone like me who was, an experimentalist, at Cambridge and the LHC, I'm going through Matthew's talk and I'm like, there's some things in there that I don't know about. This is difficult stuff.
But at the same time, I think this is just a continuing process, because I think there are very sound cases for all these different machines that people are talking about. The European strategy process, the US strategy process, other, like Japan has plans as well. There is a very solid physics case, but then how we best communicate what our physics goals and why do they justify certain, still have to work on. And it's not necessarily even always that we have to have the perfect elevator pitch for all these things. It's also when you kind of communicate with these intermediate layers of whoever wrote the BBC article, the byline is there. But like when we talk about lots of these different things and somebody hears Matthew say the word dark vector, it's pretty sexy and fantastical and things like that. And so naturally these things might get latched onto more. Whereas the bread and butter physics, which really is allowing us to advance an order of magnitude or more deeper in their nature, that's the public to understand going for those.
Do you think, Matthew, and I know this is something I've talked to Patrick a little bit about this in the past, so I'll get his opinion on it as well. As particle physicists, has our messaging been good enough? Have we made a kind of problem for ourselves with previous messaging? Like, for example, at the LHC, I saw when it was turning on and I was kind of doing my PhD, lots of messaging about we will find Susie, we might find micro black holes, we might find extra dimensions. Did we not necessarily make it clear that discovering the Higgs and that potential Higgs portal was such a big thing that now people feel a little bit kind of shortchanged by the LHC?
Yeah, it's a very difficult question. I personally, I don't want to talk about, I started my PhD in 2007. I don't really want to judge anyone from before that.
No. We're not judging anyone. It's just,
various components. I'm just going to speak on behalf of, I'm not going to speak on behalf of theorists, so I'm going to speak about theorists. Various components of the theory community before the LHC switched on were very excited about various different things, and they were right to be, because there were some very interesting theories on the table, some very big open questions, and we're all, including the general public, drawn towards the notion of conceptual revolution, whether that be supersymmetry, extra dimensions, discovering dark matter. Conceptual revolutions are really exciting moments in history.
When anyone asked me about this before the LHC, when I was doing PhD, it was like, I was talking about the same thing. So it's not a case of saying, we know amazingly well. Everyone falls into this trap.
Yes. And so when scientists are excited about the possibility that enthusiasm is infectious and it spreads and people also get excited about it. Personally, I think maybe what could have been communicated better after I started my PhD, so I want to put myself in the same bucket of blame, is that we could have better communicated how we get to conceptual revolutions. Yeah. Sometimes it's a bit of a longer road, sometimes it's very quick. And we can't make any guarantees about that. So personally, I think if we continue to study the properties of the Higgs boson, all of these different, as Patrick really well explained, right, that these machines are really multi-purpose tools that are exploring lots of different things. I think we will come to a better understanding of our universe, and I think that could well involve a conceptual revolution, but it might just take some time. Who knows? We might switch on the FCC and measure a Higgs coupling deviation that is, if something were 2 sigma, a 2 sigma deviation at the end of the LHC running, extrapolating to the precision LHC could get, within a few years of FCC running in the Higgs mode, that could become a 10 sigma deviation, and then we would all be.
We experimentalists would have said you guys, in theory, would have done a lot of ambulance chasing between the end of the LHC on that 2 sigma and the before the 10 sigma came, you'd be ready.
No, 2 sigma, no one takes, this is my point, right? This is how I want to illustrate it. 2 sigma, no one takes that seriously at all. And yet it could be an underlying, by the end of FCC Higgs run, that could be an underlying 15 sigma deviation, just sitting there waiting to be found. And so it is possible that one could have a revolution in that sense relatively quickly. But I don't think anyone should apologize for being excited. No. But I do think conveying sometimes how we get to these great big breakthrough moments maybe could have been spelled out a little bit.
So should we have made it clear, Patrick? I'm pretty sure Matthew would agree with this, but should we have made it clearer that this discovery of the Higgs boson was just the beginning of studying electroweak symmetry breaking and going further in terms of precision? Should we have made that message clearer when we were when the LHC was coming online?
Yeah, I mean, I think a fair way to view it is we had kind of an inkling that the Higgs was going to be there, as I said, from doing some of these measurements ahead of time. I mean, there was still a lot more possibilities that was narrowed by the LHC. But at the same time, why people sometimes went after these very big, a lot of them were also still tied to the Higgs, but the Higgs was kind of the afterthought. And it was the bigger conceptual revolutions that everyone focused on. And now we've found the Higgs, we still have all these same fundamental questions, but now we know it can't just look exactly like these things people were talking about 20 years ago. Everything has to be a little bit more nuanced. And so by people, if we had better explained that some of these conceptual revolutions were really still linked to problems about the Higgs, maybe there would have been a better through line for saying that we're really trying to understand basic questions of electroweak symmetry breaking. But I think, like Matthew said, like understanding the process of what we're doing, understanding what goes into it, and last but not least, I think making a bigger deal out of what the Higgs actually represented rather than just like a checkbox or the center of a circle or something. Just scratching the surface, it's hard. We have to do this next layer. And one last thing I'll just say about this kind of concept of what electric symmetry breaking could be. Like we've mentioned that the Higgs could be like a pion. There could be some underlying constituents there. I mentioned kind of this BCS theory for superconductivity. We know Higgs is not going to look exactly before, okay? There's enough wrinkles, enough things that look standard model-like that it has to manifest in a different way. So we do these experiments to kind of get us a better understanding of what could be there and what could not be there. And I go back to this Landau Ginzburg picture because we have the same picture that you're showing here of the potential, essentially. And yes, we found out what the underlying description was 5 years of the original Landau Ginzburg theory. But there was this whole other scenario of you could take this same phenomenological model, kind of a guess for what it looked like. And when you coupled it to electromagnetic fields, there was the type 1 superconductors that we explained very, very quickly. But the type 2 superconductors, which the LHC is really indebted to the fact that they exist, we still, almost 70 years later, don't have action of microscopics, okay? People think now there's phenomena for exchange in condensed matter systems, but it just shows the time scale for these things, that even if you have some basic thing and you found like the first station or the first moments around the vacuum, it can take decades. And that's in a scenario where you can just take materials and play with them, not have to build these gigantic microscopes. So
we know the ocean is there, but we've only
explain.
Yeah, we know the ocean is there, but we've only kind of dipped our toe into it so far. One thing I want to clean up, because I know we've got a hard cut off in sort of 10 minutes or just over 10 minutes. One thing I want to clean up, Matthew, is and Patrick has mentioned this to me, that you can kind of get away with doing a lot of the FCC part of the FCC program with the current LHC tunnel. And a lot of the £12 billion cost for the FCC is digging the new tunnel. So essentially the cost is all wrapped up in the FCC HH later. Do we think that's a problem, or do we need both of these FCC EE and FCC HH to pursue the Higgs and do all of this precision physics? Is there reason for people to complain that you're kind of smuggling in the FCC HH behind the FCC EE?
So first of all, I don't think Patrick would have put it the way you put it.
He probably didn't. I'm putting words in his mouth. We'll come back to him afterwards. Don't worry.
I imagine he was being more specific about certain elements of FCC. So for instance, the thing that we want to do is build a Higgs factory. And if you tried to put a LEP-like Higgs factory in the tunnel, the LHC tunnel again, you would only do something like, I mean, I'm sure there are different studies, but I would estimate something like a factor 2 better than the LHC on Higgs couplings. And that's not very exciting. And that does not get down to this level of precision we require to be able to answer these big questions about compositeness and so on. So that's not an option. Okay. And similarly, the WW and top runs would be even more challenging. You could do, again, not as well, you could do a Z run with very high statistics.
I think that's what Patrick was talking about, actually, the kind of Terra Z with high statistics. I probably just absolutely butchered the quote that he sent me. That's why. That's
okay. No, it's an important question.
You could do a Terra Z run, not as well as FCCEE, and you would get some good science out of it, but you wouldn't answer those big questions about the Higgs that we want to answer. And so, is the tunnel, really linked to the FCCHH cost, and we're sort of smuggling that in? No, in the same way that, the LEP tunnel, they dug it they were smart enough to dig it with a big enough borehole that you could fit a proton collider in later if you wanted to do it. That was not decided at the time of the lab digging of the lab tunnel, even though the foresight was there that or you build a precision E plus E minus machine in this tunnel, and then you want to have the option to go to protons afterwards.
Yeah.
It's the exact same logic there. Would we say that the lab tunnel cost was for LHC but smuggled in? No, I don't think so. And the case is similar here for FCC.
Patrick, do you want to follow up on that quickly before we come to our last question?
Sure. I mean, again, it depends on kind of what constituency you're talking to. But I think the other thing that's really crucial about the FCCE program, though, is the tie to the HH, because it isn't exactly a redo. I mean, it's a redo in philosophy of LEP LHC, but the Higgs is very different than the Z. So we're going to gain an enormous amount of physics from the FCCE program. But there are still questions that we're just not going to be able to answer yet with FCCEE that require us to keep going further in the future with an FCCHH. Now, we might get lucky and we might find something earlier on, but just the nature of the Higgs really requires this either two-step program, or other regions have a philosophy of building like a linear collider to get to higher energies with E plus E minus.
Or the muons in America, maybe.
Collider. Yeah. So I think it's important to remember that we talk about Higgs factories as a first step, which is kind of endorsed universally as the next priority. But we also have to remember that this next step after is not just a luxury that maybe we'll get to. We really need to be planning of how to get to these high energies, whether it's through FCCHH or whether it's for muon collider now, because these projects take many decades to get there, and the Higgs is just a new particle.
I completely agree, which is also why it's important, say, FCCE is built, that we continue to look we continue to endeavor to understand what is possible on different fronts as well, which is why muon collider research is also very important.
Well said. So I've got one final question, because I know Matthew has to run off for the kids very shortly. So the elevator pitch, you mentioned the words earlier, Matthew. You didn't know how prescient they were going to be, or was it Patrick? I can't remember who said it. So one final question: what would be your 30-second elevator pitch to Elon Musk, potentially, to drop 12 billion out of his back pocket and to excite the public about where their taxes are potentially going if they are going to pay for an FCC? How would you pitch that? You've got 30 seconds in the elevator with Elon Musk, Matthew. Why are we building an FCC?
Okay. I'm assuming Elon doesn't know much particle physics. I bet he probably does, to be honest. But I'm assuming. I
think he probably thinks he does, so that might help.
I bet if I mentioned quarks and things, he would know.
He'd probably know that, I'd imagine. Yeah.
But I'm assuming he doesn't here. So for me, I think that we're obliged almost after the discovery of the Higgs boson to aim to deliver really ambitious, unbiased and broad exploration of the Higgs boson and beyond, for ourselves, but also for future generations of scientists who will have big questions that need answered, and they will need the tools required to answer them.
Lovely. Patrick, do you want to have a go? Shall we put you in with Jeff Bezos?
Oh, Lord.
I don't know if that's better or worse. I'm not sure.
This entire line of inquiry we've had has been going on for centuries and millennia, that every time we kind of peel back layers, look at shorter distances, we've always found something that tells us more about ourselves, where we're going, where we came from. And so continuing this through line of human civilization is incredibly important. And we've found this next layer with the Higgs, and it really gives us kind of a milepost of that we're not completely shooting in the dark. We really have the purpose to go to shorter distances, and we now have a tool with the Higgs to exploit it. So that would be my pitch for it. And the one thing that we haven't touched at all, which is you put a $12 billion price tag on this, but it's not just a matter of you spend this money and you either find something or don't. All of these things influence technology development. They go back into the resources of the area wherever these machines are. I think when you look at actual return on investment, these are some of the best sort of science projects you can actually invest in for their returns. And the real public perception problem that we have is that it's, oh, you're putting $12 billion into a hole, and either you come back out with a particle for that $12 billion or you don't. And that's really the wrong argument that we see on Twitter or X and these kinds of things that we need to change.
I wanted to focus on the physics case today, but you're right. There are other questions and other factors which suggest we should be doing this. Gentlemen, I'd like to thank you both very, very much for taking the time today and going through those questions with me. I learned a lot. I really, really enjoyed it. And hopefully people can understand now a little bit better why we're digging this hole, as Patrick put it, and why it's so incredibly important. So I'd like to thank you again. If there's any other work or any way you'd like to point people, you can do that now. I'll make sure all of your work and links are down in the description. Any way you'd like to point people to learn more about the FCC as we close up? Matthew, I'll come to you first.
I could send you some links after.
Send me some links and I will put them down. Matthew's got a lovely talk. I don't know if you have a kind of public facing talk as well. I'm sure you probably do.
No, I don't.
I can find those and I'll put those all down in the description. Patrick?
Yeah, I think you probably already covered many of my links at other times. But
Copy and paste all those across. Any others?
Yeah, no, I think just emphasizing about the SNOMAS and P5 process and then the European strategy, that they're really, I mean, sometimes people view this field as dead and we're kind of just going bigger, but FCC is a great idea, but there's lots of other ideas out there. And kind of as we continue as a field endeavoring in this, kind of making sure that people understand that this is not just one monolithic pursuit. There's lots of things out there that we're working on.
Where's that plot, Patrick? The muons being better than the well,
there's no FCC plot on that, so
okay. Well, we'll come back to this on another day. You're right. We need the other plot. So. Excellent, gentlemen. I'd like to thank you again. I know you've got to run off, Matthew. Thank you so much for taking the time today, and hopefully the next time some consternation comes up in the press, we can get together and have another chat.
Sure.
Excellent. Thank you very much. Take care. Take care. Bye now. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.